This talk presents an RNN implementation of task dynamics, and I'm going to show how you can learn gestural parameters in activation with this model. First, what is an articulatory gesture? In some contexts, it's a movement. In other contexts, it's a goal-oriented task. Sometimes it's a system that exerts a force on the state of the vocal tract, or a period of time in which a force is exerted on the state of the vocal tract. It can even be an elemental unit of a communicative code. It can be any of the above, and we use the word in a lot of different ways. In all of these cases, gestures are conceptualized as events which have temporal bounds. What does it mean for a gesture to be temporally bounded? It means that it has a beginning and an end, which we conceptualize as locations in a space, which metaphorically represents time. The time and space metaphor allows us to refer to the temporal locations of gestures and to describe them as having regions of overlap. A somewhat different way of thinking about gestures is to think of them as systems that have states which are continuously defined at all times. The system's conception of gestures is more consistent with the Saltzman and Munhall 1989 task dynamic equations. Here I'm showing the damped-driven harmonic oscillator where x is a tract variable. Notice that there are time-varying damping stiffness in target quantities which are determined by the time-varying gestural activation states. Hence, gestural activation has to be defined at all points in time. If we insist on having gestural activation intervals, it requires a threshold in order to define them. Whenever the gestural activation is above this threshold, we identify the bounds of an activation interval. Saltzman and Munhall used the threshold value of 0. Something that's important to keep in mind is that it's easy to conflate the system with its product. Gestures are systems and they exert forces on the state of the vocal tract. Activation intervals are periods of time in which that force is exerted. These are the products of gestural systems. Saltzman and Munhall recognized that the form of gestural activation functions is unknown. They use stepped activations for simplicity, but other possibilities are no less plausible. Indeed, one might ask, why not allow for arbitrary gestural activation functions, such as the one shown here? Often when we pursue analyses of empirical measures of articulation, we assume knowledge of which gestures occur where. So if we expect, for example, a labial closure gesture, we'll look at extrema in derivatives or accelerations or use threshold criteria in order to identify a gestural onset which we believe to be present. But often there are changes in tract variables that are not associated with expected movements or gestures. How can we study these if our models don't generate them? The idea pursued here is that we can optimize a continuous gestural activation function that generates the tract variable dynamics that we observe empirically. The first step in this is to use a recurrent neural network to learn gestural activation functions. The second step, which I don't pursue in this talk, is to subsequently impose thresholds on the activation functions in order to identify events that we might call gestures, rather than impose these thresholds on the tract variables themselves. The optimization approach here is to learn a gestural activation function in gestural parameters using backpropagation in a recurrent neural network. Why not use more standard optimization approaches? Well, the activation functions we have are very high dimensional because they have a value defined at each point in time, and moreover, they should be moderately smooth. To better explain how we can learn an input function with a recurrent neural network, I want to start with a toy example. Here I have the following system, where we have an exponential decay in periodic driving force. The analytic and numeric solutions of the system are shown in the graph. The numeric approximation can be obtained with Euler's method. We have a small time step dt, and we specify the initial condition. We approximate the value of the function at the next time step by adding to the current time step our small step times the tangent of the function, which, as you'll note, is the right-hand side of the system equation. An RNN implementation of Euler's method is shown here. We have an input node, which is d of t, and we have the output node, x of t. The recurrent connection represents the dependence of x on its past value. I've also shown a loss node here, which we'll use for backpropagating error. Furthermore, in order to learn an input function that generates the appropriate output, we reconceptualize the input as a parameter, and then we use backpropagation to optimize. As a side note, a convenient way to visualize an RNN is to unfold it, where we think of each time step as a layer of a deep network. This is shown on the right. To optimize, we first conduct a forward pass where we calculate the loss, which is half the squared error, which is the difference between the model output, which is the blue line, and the target output, the yellow line. The error here is the purple line. Note that the initial guess that we use for the input is 0 at all times. To figure out how we should adjust the input in order to decrease the loss and diminish our error, we calculate the gradient of the loss with respect to all inputs and parameters. Essentially, we do this by following backwards all of the paths in the network. Here I'm showing the partial derivative of the loss at time t plus 2 with respect to the input at time t. And notice that this is calculated using the chain rule, which consists of partial derivatives, each of which can be associated with one of the connections in the network. To implement this, we loop backwards through time and accumulate the error for each node. After we finish accumulating error, we update the parameters using lambda as a factor to control how quickly we change the parameters. We iterate the forward and backward passes, each time updating the input. And by the final iteration, we have a very small error gradient, shown with the black line here. The error is effectively 0, shown by the yellow line. And notice that the model output and target output are nearly indistinguishable. And finally, we started with initial guess for the input of 0, the black line. But by the final iteration, we've learned the correct input, which was sine of t. So to review what we did, we had a known system with a known input and output, but we then pretended that we did not know the time-dependent term, the input, and we reconceptualized it as a time series of parameters. We implemented an RNN to numerically solve the system, analogous to Euler's method, and we used backpropagation to iteratively adjust the parameters. As a result, we obtained an approximation of the input function that makes the system generate the correct output. Importantly, we can do this for the task dynamic model as well. If you're interested in further references on using RNNs to solve ODEs, here I have provided some. The task dynamic model posits the second-order differential equation for the evolution of tracked variables. And recalling Newton's force equals mass times acceleration, we can express this as a combination of forces that are acting on a tracked variable, which include a damping force, a restoring force, and a driving force. We can further simplify this by making an assumption that the system is critically damped, and moreover ignore inertial effects by setting m to 1. To implement the solution, we convert the second-order equation into a system of two first-order equations by defining y equals the derivative of x. There are some important differences between the RNN model I'm presenting here and the task dynamic model. One is that the RNN model has no model of articulators. It only models gestures and tracked variables. A second important difference is that the RNN model has a different conception of the neutral tractor. Consider that in the task dynamic model, the neutral tractor applies to articulators when there is no influence of an active gesture. This requires a threshold and thereby imposes temporal delimitation. In the RNN model, neutral tractors specify a default state for tracked variables rather than model articulators. There will be one neutral tractor for each tracked variable system, and these will have a constant low level of activation. Moreover, the dynamic parameters of tracked variable systems, time-varying stiffness and targets, will be weighted averages of gestural and neutral tractor parameters. Note that gestures and neutral tractors are effectively treated identically by the model. Here the neutral tractor activations will be fixed rather than optimized. Here's an overview of the structure of the model. At the bottom, notice that we have input vectors of gestural activation, one for each time step. We also have stiffness and target parameters, one for each gesture. These are weighted according to their gestural activations to determine the dynamic target and dynamic stiffness, which we see in 1 and 2. The dynamic target and dynamic stiffness in turn contribute to the current tracked variable velocities, which influence the positions of tracked variables we see at level 4 of the network. The loss is 1/2 the sum of squared differences of the target output and the tracked variable positions. Here are the model equations. Here are some examples of how parameters and gestural activation influence the forward dynamics of the model. Let's start by comparing the blue and orange lines. Both of these are step gestural activation functions, but the orange line corresponds to a gestural target of 0.75 and the blue to a gestural target of 0.95. Notice then that the dynamic targets are different when the gestural activation is at 1, and the profiles of the position and velocity signals are different. Another comparison to make is between the yellow line and the blue line, where the yellow line has sigmoidal ramping. You can see that the sigmoidal activation ramping has effects on both the velocity and position of the tracked variable, as well as the dynamic target and dynamic stiffness. Finally, examine the purple line, whose gesture activation is 1/2 of the maximum. This also has effects on dynamic stiffness and target, velocity, and position. In order to optimize the gestural activation functions and the parameters, we use the backpropagation algorithm that we illustrated earlier in the toy example. Slightly more complicated here in that we're backpropagating error associated with both position and velocity through time, which you can see with these magenta lines. And furthermore, we have the target and stiffness parameters being shared across all time steps. So we accumulate error associated with those for each time step in contrast to the gestural activation functions. The data set used for this study is from an experiment that used a visually cued prepared response task with a sustained pre-response vol E. On each trial of the experiment, the subject saw a target cue and sustained a pre-response vol E until a green box appeared on the screen approximately 1.5 seconds later, at which point the subject produced the target response, in this example, pop. There were 9 response categories in the experiment, which correspond to all combinations of PT and empty onset and coda with the intervening vowel ah. The orthographic forms used to cue these are shown in the table. In implementing the network training, a time step of 1 millisecond was used, and different learning rates were used for gestural activation in stiffness and target parameters. The relative values of these learning rates may result in different outcomes, and this is an area that needs to be investigated further. We will compare the effects of 2 different strategies for setting initial activation functions. One is zero initialization, in which we set all activation functions to 0 prior to the first iteration of the algorithm. The second strategy is gradient-based initialization. Here we begin with the derivative of each tracked variable that's associated with a given gesture. If the gesture specifies a target that is 0, we change the sign of the derivative. We then apply linear rectification and rescale from 0 to 1. The intuition behind this is that when there is a change in a tracked variable toward the target of a given gesture, it suggests that there is activation of that gesture. Subsequent analyses will be focused on effects of these initial activation function strategies. We will examine loss distributions, how good are the model fits. We will conduct qualitative analyses of example trials and examine target and stiffness parameter distributions and correlations of those parameters. Secondly, we'll examine optimized gestural activation functions and ask what they can tell us about gestural activation. First, the loss distributions obtained with both zero and gradient-based initialization are very similar. Moreover, the losses of individual trials are highly correlated between the 2 initialization strategies. This entails that when there are poor quality fits, these are due to trial properties rather than differences in initial activation. It's important to note that the fits are generally very high quality. The zero initialization scheme provides relatively smooth activation functions and dynamic stiffnesses. Compare this with the gradient-based initialization, where the activation functions are somewhat less smooth, and this results in more fluctuations in dynamic stiffness and target. When we overlay the zero and gradient-based initializations from this trial, we can see more clearly these differences. Another interesting difference involves the activation relations between antagonistic gestural pairs, such as bilabial closure and bilabial opening or release. Notice that with zero initialization, we see complementary activation of antagonists. When lip aperture closure is highly active, the bilabial opening gesture activation is very small. And conversely, when bilabial opening gesture activation is high, bilabial closure gesture activation is low. That pattern contrasts with the gradient-based initialization, where we can see that antagonistic gestures are coactive. When there is a peak in bilabial closure, there's a smaller peak in bilabial opening, and vice versa. With a peak in bilabial opening, there's a smaller peak in bilabial closure. This holds for the other gesture activation functions as well. In the top of this figure, we have tracked variables and then the 6 gestural activation functions comparing the gradient-based initialization, dotted lines, with zero initialization, solid lines. And we can see that there are generally higher levels of activation or higher activation peaks associated with gradient-based initialization. This is probably due to the coactivation of antagonistic gestures. a given gesture has to have more activation when its antagonist is also activated in order to achieve the same target. Another consequence of the coactivation of antagonists is that given gestures such as bilabial closure tend to have biphasic profiles associated with an onset or coda constriction. Here we see distributions of parameters for target and stiffness for all 6 gestures after they've been recentered by participant. For zero initialization, we see a high degree of consistency in these parameters across the 9 response categories. In contrast, the gradient-based initialization results in more between response category variation in target and stiffness parameters, which are plotted here on the same scale as in the previous slide. One phenomenon that arises in the optimization is what I will call parameter pinning. This is observed with both initialization strategies, and it occurs when a parameter's value is pushed up against a floor or ceiling which is imposed in the optimization. For example, all gestural target parameters are constrained to fall in the range of 0 to 1, which are the bounds of each normalized tract variable. Thus, in some cases, we see that these parameters get pinned to that floor or ceiling. One participant, PL1, had all of the bilabial closure target parameters pinned to the floor, whereas for other participants, we see that in some response categories, these parameters were pinned, but not in all response categories. Notably, parameter pinning was most extensive for the tongue-body high vol gesture. When we examine correlations between parameters, for the zero initialization scheme, we observe that they are relatively weak. All of the correlation coefficients are fairly mild in this case. In contrast, with gradient-based initialization, we see some strong correlations between stiffnesses of antagonistic pairs of closure and opening gestures. An important question to address is, which of these two initialization strategies should we prefer? Consider that they had nearly equivalent loss distributions and both produced very high-quality fits of the empirical data. An argument in favor of the zero initialization strategy is that it's more parsimonious. It doesn't require us to use the empirical tract variable data. Notably, zero initialization resulted in complementary activation of antagonistic gestures. This is perhaps a reduction of entropy in the gestural system state, since the correlation is stronger than observed in the gradient-based case. On the other hand, gradient-based initialization gives us coactivation of antagonists, which in some ways resembles muscular control and may be more stable. Another argument in favor of zero initialization is that it results in more consistency in parameter values across our response categories. This is desirable if we prefer a more parsimonious account of the long-term memory of gestural targets. In the following analyses, we will examine gestural activation functions in more detail, focusing only on the zero initialization derived functions. In this figure, I'm showing average activation functions for bilabial closure and bilabial opening gestures for pa, ta, and empty onset responses. Observe that when we expect a bilabial closure to be present, as in the pa response, we see a peak in the gestural activation function for bilabial closure, which is not present in the other response categories. Notice also that there is a cross-participant variation in the activation of the bilabial closure that occurs after the response. This is likely attributable to the fact that different participants adopt different bilabial postures after producing the target response. Another interesting feature of the data is that there is non-zero activation before the response, during the sustained pre-response vowel E. This non-zero activation may reflect the fact that the lower lip is raised via its mechanical coupling to the jaw, which is in turn raised in order to support the production of the high front vowel E. Alternatively, this could reflect active posturing of the lips during this time period. Another thing to note, and here I have zoomed in time on the gestural activation functions, is that the average profile of activation peaks is relatively symmetric and quasi-Gaussian. Here I'm plotting phase portraits in the temporal vicinity of the onset constriction gesture of bilabial closure activation against bilabial opening gestural activation. The L shapes, which show first an excursion in the horizontal dimension, an increase in bilabial closure activation, followed by an increase in the vertical dimension, which corresponds to bilabial opening gestural activation, indicate that there is a high degree of separation between the closure and opening activation peaks. This same high degree of separation or complementarity is also observed for the tongue tip closure and opening gestures. Here we are showing average bilabial closure and release gestural activation functions for the response categories with a bilabial closure in the coda and showing the three different onset conditions. Notice that the heights of the activation peaks for the gestural activation associated with the coda constriction differ as a function of the presence of the onset constriction gesture. Specifically, we have cases where there seems to be hyperactivation of the bilabial closure when it also occurred in onset, as well as cases where there is hypoactivation of the bilabial closure gesture when it was present in the onset. These effects are also observed with tongue tip coda constriction gestures. The origins of these effects are unknown and may indicate that we need additional mechanisms in our model. However, the interpretation of such effects is complicated by the fact that some differences in activation may be artifacts of mechanical coupling. For example, when we look at tongue body gestural activation for the high and low vowels, we see that there is a greater degree of activation for the high vowel tongue body gesture when the initial onset consonant is an alveolar stop. This may be because the jaw contributes to the raising of the tongue tip in production of the alveolar stop, and thus has effects on the tongue body as well. Since the model doesn't distinguish between articulators and tract variables, it is likely accomplishing the change in the tongue body tract variable via gestural activation. Relatedly, we can see that there's a higher level of gestural activation for the low vowel tongue body gesture for the response categories that are onsetless or have a bilabial closure onset. This may again be because the tongue tip raising associated with alveolar stop onsets has mechanical effects on the tongue body. Note that as with lip aperture in tongue tip gestures, for the high vowel and low vowel antagonistic tongue body gestures, we also see a high degree of phase separation in gestural activation phase portraits. One future direction of this analysis is to reduce dimensionality of the gestural description by developing methods to automatically detect gestural events. However, this is complicated by the fact that the model doesn't distinguish between active and passive movements. For example, Consider a response pot, which we see tracked variables of here in the optimize gestural activation functions in the 3 panels below. Notice that we have bilabial closure gestural activation during the period of time associated with the coda. This is not because we have an active bilabial closure gesture, but likely rather because the lower lip raises due to its connection to the jaw, which is in turn playing a role in producing the tongue tip closure, for which we also see gestural activation. Other examples of passive effects are illustrated here as well. A possible solution to this problem, which is under development, is to incorporate a model articulator level into the network. Loss would be calculated at this level, and we would include weights that map from tracked variable changes to model articulator changes. These weights would be optimized via backpropagation. Note, however, that this architecture would be slightly different from the task dynamic model. Another extension of the model which I've been developing is to model the encoding of gestural targets with spatial fields that receive excitatory and inhibitory input from gestures. In this model, there are not gestural stiffness parameters, and instead, the stiffnesses of tracked variables are calculated from integration of activity in the target planning fields. Ultimately, it's important to ask why we might want to derive continuous gestural activation functions using this method. First, recall that continuous gestural activation is more consistent with the task dynamic model and requires fewer assumptions about theoretical entities. Specifically, it doesn't require us to impose arbitrary thresholds on gestural activation just for the sake of identifying activation intervals. Furthermore, the continuous gestural activation functions provide us new opportunities for analysis and may reveal previously unrecognized phenomena. For more information, please see the following paper available on my website. Thank you.